Hi, everyone. I'm Ashmitha Shetty. I'm a network engineer at Meta. I work on comms performance optimizations for our AI clusters.
Hi, everyone. My name is Mincy. I'm also from Meta. I'm a computer scientist working on communication libraries and transporter development.
So today, we are going to present some of the work that we did in our comms library stack, transport network, in enabling this high-performance Llama 4 training. So with every generation of Llama, we have seen a significant growth in the model size and the complexity. Last year, we launched Llama 3, which was a text-based model with 405 billion parameters and was trained on 16K GPUs. However, with Llama 4, we wanted to scale this even further. The largest Llama 4 model that we have trained so far has nearly 2 trillion total parameters. To train such a colossal model, we had to expand our AI clusters, deploying over 100K GPUs. Secondly, the number of parallelisms have also increased. In Llama 3, we had 4 degrees of parallelism. In Llama 4, we introduced a new layer of parallelism called the expert parallelism to support our mixture of expert model architecture. Furthermore, the individual parallelism factors have also scaled up by 2 to 4x. So with bigger models and changing parallelisms, we now have more traffic going out on the network. So our main challenge now is how do we scale our network and optimize our communication stack to enable training our models efficiently. So let's talk about the topology that solves these changing model requirements. Last year at Network at Scale, we talked about our 24K clusters. So if you recall, the basic building block of an AI cluster is an AI zone. To form a 24K cluster, we took 8 such zones and connected them together using an additional layer of switching called the aggregate training switches. At this layer of network switching, the oversubscription ratio is 1:7. However, since the job size has increased beyond 24K, we had to do 2 things. First, we had to build a network that spanned multiple buildings in order to support a cluster of hundreds of thousands of GPUs. The network within a DC is still a 3-layer claw architecture. We have 8 AI zones within a DC. To interconnect the DCs, we use a fully connected mesh between the ATSW layers of every building. Compared to our 24K cluster, we had to reduce our oversubscription ratio from 1:7 to 2:7. The same oversubscription ratio is maintained beyond buildings as well. This is because Llama 4 generates multiple parallel collectives, thus producing high amount of outstanding traffic on the network. So by lowering the oversubscription ratio, our network is no longer the bottleneck for collective operations. So what are some of the trade-offs of this multi-layered network architecture? On one hand, this network design helps us run jobs at over 100K scale. But on the other hand, it introduces high latency. Specifically, if you look at GPUs within the rack, they have the lowest latency, versus GPUs in different rack, in the same zone, or in a different zone, or in a different building, have nearly 7x to 15x to 30x higher latency. So this high latency introduces 2 challenges. First, we need to ensure that different parallelisms with different bandwidth and latency requirements are mapped to different layers in the network. Not doing this can affect certain parallelisms and make our model progress slower. Secondly, high latency also negatively impacts our collective performance with the existing baseline nickel implementation. This is because our existing collective library only supports a limited amount of outstanding data, which is not enough to saturate the high bandwidth delay product of our inter-building connections. So to address the first challenge, we introduced a scheduler feature called the balanced hierarchical allocation. So this provides us with the unique ability to map specific parallelisms to specific layers in the network. For example, this feature can ensure that with a tensor parallelism factor of 16, all the 16 GPUs that are involved in TP are communicating within the rack. This feature is now in production and has actively supported our Llama 4 scale. So in the previous slides, we addressed the first challenge with larger network and job scale. Now in the coming slides, we're going to look at how we address the second challenge with poor comms library performance with the baseline nickel that is made worse with high latency. We talk about how we evolved our collective library with the new algorithms and the transport stack to solve these problems. Over to Min.
Thank you, Ashmitha. So next, as Ashmitha introduced, we're going to look into the communication library stack to introduce how we resolve the rest of the problems to support our pre-training on such complex topology. This diagram shows a breakdown of our software stack for supporting pre-training. Within it, we highlighted the purple components where we made a downstream fork from NVIDIA NICO library. We called it NICO-X, which will be fully maintained by Meta engineers. Specifically, we developed a custom transport module within NICO-X called Sichuan here. We enabled the optimizations all the way from the custom algorithms and custom communication features all the way down to a lower transport level, including NVLink and high-speed Rocky network. So let's see what we have changed within it. We first introduced what NVIDIA NICO behaves. The core concept of NICO is a two-stage copy. So as shown in this diagram, we could say the NICO designs the collective algorithms based on the copy that the data will be first copied from the user buffer to an internal network registered buffer, and then goes through network to remote side to the same copy to get the data back to the user receive buffer. This two-stage copy will require GPU resources, including both SAMs and also HBM bandwidth. So the design does not only result in poor performance, either in concurrent compute or communication due to the resource contention, as we could see. It also limits the network performance tuning that we could do because the involved data chunking in the two-stage copy essentially hide the full message size to the network. One example we could tell from this diagram, you could imagine the pipeline. If we make this internal buffer be big enough, it would help us to send a larger chunk to network, so it could saturate the high latency network. However, it will expose extra copy in the pipeline. If they make this temporary buffer smaller, it will help us to hide this extra copy. However, it will limit the network transfer speed, as we previously mentioned. So we figured out this issue. We realized we need to make a big change over here. In our custom library, what we have done as the first core framework change is to change this to be a zero-copy based scheme. So now, the source NIC can directly transfer data from the source user buffer through RDMA to the receiver side user buffer without any involvement of the computing resources, including SAM, nor any HBM load store for the extra copy. This way, we could avoid any contention when the computation and the communication are happening concurrently. As one prerequisite of this zero copy, we need to enable the smooth buffer registration because RDMA needs to access the user buffer now. What we have done is to customize the PyTouch cache allocator all the way to Sichuan internal in order to enable RDM access for all user buffers. Cache allocator in general provide us good buffer reuse, so we should not see a lot of buffer being registered to network. However, in some cases, we do see the reuse is not desired, so we also provide the option for like a memory pool style thing to restrict the number of buffers that has to be used for collective and thus needs to be registered to network. This way, we could involve zero copy communication to give us good performance without adding any visible registration cost. Zero copy itself, it gives us more benefit rather than the resource contention problem. one big benefit we could get is now we can expose the entire message to network layer. So our transport can be more flexible to config the load balancing scheme, such as packet splitting, number of queue pairs, and so on. In general, we see zero-copy collective give us much, much better network efficiency when we run in production. But we do see in some cases, if there are concurrent collective happening with the too large message, the receiver side may be congested. So this will involve some specific core design from the collective algorithm layer with the lower transport performance tuning layer, which Ashmitha will introduce detail later. So in addition to the zero-copy part, another thing we redesigned in our custom library is to change the algorithm framework. This diagram showing in this picture now is the original Nico library, which drives the collective algorithms. Every algorithm will be driven by the CUDA kernel. What that means is for every single collective, you will involve back and forth GPU and CPU synchronization because the kernel has to offload every RDMA request to the internal host proxy thread. So this extra CPU synchronization happens no matter you have a zero copy or do you need a reduction or not. As a solution here, we designed a host-driven algorithm in our custom path. So now, if we compare what we were done in the right side diagram, every algorithm, if they are not involving any reduction kernel, they are fully driven by CPU now. So we can see there is no GPU synchronization happening. It gives us much better performance in general. This way also allows us to quickly adopt a lot of classical collective algorithms from the classical high-performance computing communication libraries, where we often design algorithms on CPU side. So based on those two framework improvements, we made a number of performance optimizations and custom features to support various pre-training communication requirements. We showcase some important feature here. The first thing we will add is we largely enriched the algorithms that can be selected for each collective. Altogether is one example. It's used in fully sharded data parallel domain and will require medium message size running on larger system scale. We included some log-P, log-1 algorithms to give best performance in that communication scheme. The other example we would like to demonstrate is at 100K pre-training, we may want to enable elastic training. What that means is you want the full model continue training, even where are some hosts getting fault and shut down, and you want the training still ongoing and continue. Whenever the later host come back, they can speed up the training, but there is never a time that you will shut down the full training. As of our Llama 4 strategy, we enabled this elastic training as option as the data parallel domain, where the all reduce is performed across replicas. As comes requirement, we should enable the all reduce be fault tolerant. Specifically, we want to enable timeout management, error handling management, and retry management. In the later of this session, we'll have a next talk to introduce details of our elastic training. So now let's go to the inner domains in the pre-training. In the inner domain, communication are often exposed, so we're taking care more about the performance itself. Now their copy and SM-free collectives becomes highlighted. For instance, we enabled the zero copy in a pipeline parallel domain for send receive. It allows the send receive running in full speed, even when it's overlapping with concurrent computation. Another custom feature leveraged SM-free optimization is the TP. We enabled a custom put communication operation to allow the innermost TP domain to do a fine-grained computer communication overlap so that the previously exposed collective or latency can be fully hidden with the concurrent chain computation. Thanks to their SM-free and zero-copy optimization, we don't see any contention with concurrent compute and communication here. So we won't go to many details of all the features. If we want to check some details, please go to our blog. All right, okay. I think we get a lot of details about our communication library algorithm layers. Next, I will hand over to my partner Ashmitha to introduce the training part in transport.
So now that we have covered the algorithmic innovations, let's look at the custom transport stack that we built for NICLX. Earlier, Min briefly noted some of the challenges with zero copy, specifically with how sending too much data on the network can cause congestion at the receiver end. So to address this for zero copy collectives, we developed a dynamic queue-pair load balancing mechanism that gives us better flow control and load balancing across queue pairs. With DQPLB, we can control the amount of outstanding data on a per queue pair or a per GPU to GPU basis. By tuning these parameters on a per network layer basis, we can limit the chance of incast or congestion happening on the network and also minimize the buffer buildup along the network paths. The second aspect of DQPLB is the enhanced software-based load balancing. Unlike baseline nickel, which takes a single message and splits the data across all the queue pairs evenly, DQPLB offers the ability to send a larger portion of the message on the least loaded or the congested queue pairs. This improves our ECMP performance by a large margin without even making changes on the network layer, but merely by changing our comms library stack. So let's look at some of the results of our custom transport and how it compares with the baseline nickel. So DQPLB is designed in such a way that the topology awareness is built into it. It has knowledge of where the ranks are located with respect to each other. So using this topology information, we can configure each virtual connection differently. So we provide 4 scopes, that's intra-rack, intra-zone, intra-building, and cross-building. By tuning these transport parameters on a per-network scope basis, we can achieve optimal performance on both long and short data haul paths alike. Here we present the point-to-point send-receive results with DQPLB and out-of-box nickel. We see almost line rate performance with DQPLB when we have 2 GPUs communicating in different buildings. This is something that baseline nickel cannot achieve due to some of the architectural limitations like the 2-stage copy and the lack of topology awareness. So we also tuned our transport configurations by taking the nature of collectives into account. So let's take all-to-all as an example. It's the most bandwidth-intensive collective because every GPU is talking to every other GPU. So the pure zero-copy implementation removes the copy overhead, but can potentially cause network congestion at the receiver end, or in the worst case, cause packet drops as well. By carefully tuning the transport parameters, we are able to achieve a good balance of throughput without flooding our network. This has helped us achieve almost 20 to 50% better benchmark performance and about 10% end-to-end model performance. In the future, instead of statically tuning these parameters on a per network hop or a collective basis, we would like to work on auto-tuning these parameters. So back to Min to finally conclude the talk with some key takeaways and a future work.
Well, thank you, Ashmitha. So what's next? We are still in the middle of model and hardware innovation to support large language model training, as we are very interested over here. As the rest of this year, we are enabling resource-efficient communication, such as SM-free support, but over a much larger scale-up domain with high-speed NVLink connection. For the model renovation side, for serving those gigantic models to end users, we need to optimize collectives generated in our inference workloads now. It may over NVLink or scale-out domain. As a difference compared to the pre-training side, the inference workloads give us some new requirements, specifically optimizing low latency communication and very fine-grained computer communication overlap may need a custom communication library support. For the coming year, the model growth continues with a much higher possibility to challenge the limited capacity that we could have, and would end up require training maybe with heterogeneous accelerators located in different data center regions. So as our comms team, we are actively preparing for that, for supporting the required heterogeneous and long-distance communication. Last a few seconds to summarize the takeaway from our Llama 4 experiences. We believe communication and network innovation is a key investment to support large language model training inference. As demonstrated in our Llama 4 experiences, the accumulated communication features contributed more than 15% end-to-end training efficiency and also enabled inelastic training that would keep the training at a very high good-put ratio. Our experiences demonstrated that the power of cross-layer design from model to comms library and within multiple layers within comms library would be a key successful approach, allowed us to provide process support and deliver into production at scale smoothly. The ongoing and future language model requires diverse communication support, as we could see new feature requests coming out every year. A unified communication stack sits as the successful foundation to support that diverse communication requirements rapidly, effectively. So there are more to come in the coming heterogeneous training era. We look forward to that. Thank you, everyone.